The last thing that I'd like to do here in this section is just to quickly summarize a lot of the main ideas that we talked about. 4.3 is a very dense section. There's a lot of information. All of it's important, but I want to take some time here just to quickly summarize and give a quick overview of the main ideas that we talked about in 4.3. First up, this is something that we didn't actually explicitly state, but it says if f is differentiable on an interval, then f is a smooth curve. And I'm glad we're going to talk about this here. If a function is differentiable, what that really means is that the derivative exists. So if the derivative exists on an interval, then f is a smooth curve. And hopefully this makes sense if we think about it. If we think about places where the derivative does not exist, we gave some graphical examples. We said sharp corners, or discontinuities, or cusps, anything like that. We know we won't be seeing if we're working with a differentiable function. And the majority of the functions that we work with will be differentiable because we spent so much time trying to learn how to take the derivative. Well, the derivative better exists so that we can actually use it. We like to work with differentiable functions. We like to work with smooth curves. They generally make doing cool calculus stuff a whole lot easier. The next two talk about the sign of the first derivative. Here it says if f prime is greater than 0. So here another way for me to say that is if f prime is positive on an open interval, then f is increasing on that interval. So we saw this going back to the very beginning of this section. We said, hey, if we look at the sign of the first derivative, it can tell you whether your function is increasing or decreasing. And similarly here, if f prime is less than 0, so what I can say there instead is if f prime is negative on an open interval, then f is decreasing on that interval. So it's really the sign of the first derivative that tells us a little bit about the behavior of our original function. The first derivative can tell us whether our function is increasing or decreasing. And when we have a sign change in our first derivative, so if f prime changes sign at any point, then we know we either have a local maximum or a local minimum, assuming that f is continuous at that point, I should say. But generally, if we have a change in sign, say from positive to negative, then we will have an a local maximum. Or if I change from negative to positive, in that case, I would have a local minimum. So those local extrema will always occur whenever we have a sign change in our derivative. That's what we're looking out for. Similarly, we can also find local extrema using the second derivative test. However, this is only going to work if f prime is if f prime is equal to 0. So if we have a horizontal tangent line, remember, f prime is equal to 0. That's really what that means. We have a horizontal tangent line. If we have a horizontal tangent line and the second derivative is less than 0, another way we can say that is f double prime is negative. Well, if f double prime is negative, we have something which is concave downward, which means we must have a local maximum at this point where we have that horizontal tangent line. Similarly then, if we change the sign on our second derivative, so if instead f double prime is positive and we have that horizontal tangent line, if we sketch in and we say, okay, here's what the graph of a concave up function looks like, that's what f double prime is positive really means. Then what's going on at this point right here? Well, I've got that local minimum occurring at that horizontal tangent line. But the second derivative can also tell us about concavity. So if f double prime is greater than 0, so again, if f double prime is positive on some open interval, then f is concave up. I'm going to underline concave up here on that particular interval. So I might have something that looks like either one of these curves right here. I might also have that parabola shape. I could just have a regular old parabola. That's an example. Y equals x squared is an example of a graph which is always concave up. And if I change the sign on my second derivative, if my second derivative, f double prime, is negative, in other words, if f double prime is less than 0 on some open interval, then f is concave down on that interval. Here we're looking at either this curve or this curve, something that looks like that, or again, we could just have say the graph of y equals negative x squared. We could have sort of both of those put together. That is also a graph which is concave down on that interval. So if we're looking for concavity, we're looking at the second derivative. And then finally, if we have a sign change in our second derivative, so if f double prime changes sign, here in the graph we have something which is concave up. It might be a little bit difficult to see, but here we have something which is concave up. On the right hand side we have something which is concave down. That means that this point right here is called an inflection point. So anytime we change concavity, it doesn't matter whether we're changing from positive to negative or negative to positive. Any sort of sign change in your second derivative, so long as the function exists there, will be an inflection point. We're not going to distinguish between changing from negative to positive or positive to negative. These are a little bit more subtle, and we'll get to see more of these in the next section. We'll get to see all of this stuff in action in the next section, because we're going to be taking all of this information, kind of putting it together and saying, okay, if I have this as a function, let's see if we can tell everything about it. So we're going to look at the first derivative. We're going to look at the second derivative. We're going to look at the original function and the domain. And we're going to see, okay, where is this function increasing? Where is it decreasing? Or does it have any local extrema? Where is it concave up? Where is it concave down? Does it have any inflection points? We're going to put all of these skills together, and then at the end of this process, we're going to say, okay, we know all this stuff about our graph. What does that look like then? We're actually going to practice sketching the graphs of these functions. So take a look at that section. It's a good section to look at it too if you're still feeling a little bit uneasy about finding some of these points, because we're going to be practicing finding local extrema and concavity and points of inflection. All of that we're going to see again in section 4.4 in the next section.